In this experiment, we'll try to know more on OFDM, like how it is being implemented, and also obtain or estimate the channel frequency response using the function which is already available in WLAN toolbox, that is WLAN LLTF channel estimate. Here it makes use of the LLTF field of the packet preamble in order to obtain the channel frequency response on occupied subcarriers. And second point or second method is I have written a own script using a simple least square channel estimator in order to compute the channel estimate and compare these two. And lastly, what I do is I'll obtain the DFT of the actual channel impulse response and see whether the channel frequency coefficients which is obtained in the two methods, that is using a WLAN LLTF channel estimate and the own script, does it matches to the DFT of the channel impulse response. So we know when you take the DFT of h of n, you get h of k. So using this fact, I just want to verify whether the channel frequency response obtained in the first two methods matches to the DFT of the channel impulse response. So in this experiment, some of the things are repetitive. There I would not emphasize more on that particular part, and I would like to emphasize on few things which is being or the functions which is being written newly for this particular experiment. So here main objective is the LS estimation of the channel frequency response over LLT of subcarriers. So here I've created again HE packet configuration and the transmit waveform. Here again this we have come across. This is a system object which is used to create a single user high efficiency configuration format for HESU 11AX that follows the standard. And the allocation bandwidth 20 megahertz I have taken. MCS I fixed it to 8, that is 256 QAM modulation with coding rate of 3/4. And LTF type is 1, guard interval is 0.8 microseconds, and the data field is 0 because I don't do any processing on the HE data field. Just because I use only the LLTF field of the packet preamble for channel estimation. So it is, I have set it to 0. Whether you make it non-zero, it is actually it is irrelevant for this particular experiment. So again, here I'm generating a random data bits, right? And PSDU is created. This PSDU is passed into the WLAN waveform generator. This we have seen earlier and discussed. Again, if you want to get into the details, you can open this. You can right click on this and click on open. That function gets opened, and in the initial part, when you go into details, actually it is not, it's very difficult to understand actually what is happening inside. But if you can read this comments, you get an idea like what and all is being done. So actually the data is scrambled initially. When you give the data bits to the WLAN waveform generator, data bits are scrambled to randomize the data pattern for security and interference mitigation. The scrambled bits are modulated in order to form the constellation symbol. Also, the LDPC coding is employed for forward error coding, forward error correcting. So LDPC is widely used in Wi-Fi standards in 11 and ACAX. It is also used in digital video broadcasting, satellite communication, optical communication, etc., due to their high reliability and efficiency. So at the output of the WLAN waveform generator, we have a transmit waveform. That is 11AX HE single user packet waveform of size NS by NT. NS is the number of complex samples and NT is the number of transmitting antennas, and it is here we have 880 cross 1 because NT is 1. We have considered SISO model. So hint again I have discussed earlier, there is WLAN field indices. When you pause the configuration object into this, what you get to see is the index points of various fields in the packet. So in the last experiment, we have seen what is the preamble portion and what is the data portion and all. As you can see here, HE data is 0 here. I hope you can see. Yeah. And okay, I've already executed this program. So let me paste this in command window so that it is clearly visible. So LSTF, LLTF, LSIG, these are the legacy part of the preamble. And because I have not given any data, HE data is 0. The packet extension is also there here. So If you can see, this LLTF is a field which I'm interested in, because the LLTF is used for channel estimation, and this is a part of the legacy part of the packet preamble. The sample points 161 to 320 corresponds to LLTF. There are 160 samples which corresponds to LLTF. That is a legacy long training field. That is being stored in LLTF transmit. So I have a transmit waveform. In LLTF1 corresponds to 161. Then in the LLTF2 is 322. So I'm going to extract the samples from 161 to 163 from TX waveform. Therefore, LLTF transmit has 160 complex samples now. So TX waveform, as I told you, is the output of the double line waveform generator. And we know at the transmitter end in OFDM what is done. IFFT is done. So the input, the complex modulation symbols, which is obtained from the constellation points. So IFFT is done on that in order to get the complex samples. So this TX waveform is a complex sample. So this can be viewed as a time domain. The input constellation symbols, capital XK, okay, is given to IFFT. So XK is viewed in a frequency domain view. So output of IFFT, this is a time domain TX waveform, that is XN, small xn, these are the complex samples. So from this 880 samples, I'm collecting only those samples that corresponds to LLTF, that is 160 cross 1, by making use of this ind, which gives the indices of different fields. So then I'm configuring a TGX channel for 20 megahertz, large scale effect, both pathless and shadowing have enabled. The number of penetration walls is taken as 2, and for each wall, the wall penetration loss is set to 5 dB. So I've set the random stream, and then the TGX delay profile considered as model D, and the transmit receive distance is set to 10. So this TGX, what it does, it will display the channel parameters here, and you can see, so whatever is being set here, same thing gets displayed, and transmission direction is downlink default. So some of the values will have default values, so it will take this. For example, number of penetrated walls, floors, we haven't considered in this program in our simulation, so that is set to 0. So if you don't edit or change some of the parameters, that gets set to the default values. Then I'm passing this TGX waveform to TGX channel. So the output waveform is stored in TGX output, and these are the path gains. And I'm resetting TGX in order to reset to get the different channel realization every time. And here, yeah, this is not necessary actually, because I'm running the code only once. But if you, in some of the codes I have shown you earlier, where you want to visualize what is the distribution of channel frequency response, that case you are going to run the same code, or pass the waveform through the TJX channel multiple times. Then you set inside the for loop, you will have to reset. Otherwise, in practice also, when you process large number of packets, so here number of packets processed is 1, because only once I'm passing TX waveform and getting the output from the TJX channel. So here reset doesn't actually make sense, but when you process a large number of packets, yes, reset TJX is required. Then this gives info TJX, gives the information about the channel, like what is the what is the size of the channel filter coefficients, the path delays, what is the path loss, because I had enabled the large scale fading effect. So you get to see these parameters from this info function. So this is a kind of repetitive we have seen in channel experiment 1. If you are interested, please revisit experiment 1. In this, what we are actually doing is we are trying to obtain the channel impulse response from the path delays by making use of the TGX sampler rate, and taking the path gains at the first column of the path gains to the non-zero tap index values of IMPR, and then plotting the IMPR. So this is actually the experiment 1, which I've explained in detail. Please revisit that if anyone is interested. So here I'm plotting the impulse response of the channel that is a model D. So this is the first plot which I get. It's a 18 tap filter, and if you can see the maximum here, if you see the maximum spread is 390 nanoseconds, and this is the absolute, that is amplitude versus magnitude versus time. So it's a magnitude response or the channel impulse response for model D delay profile. So now the TGX output which is obtained from the channel, I'm storing it in RX waveform, and I'm obtaining again the LLTF field indices. So now from the RX waveform, I am getting what is the actually received LLTF. Okay, if you give TX waveform, earlier I think I had what was the transmitted LLTF. So from the receiver waveform, if you get the indices, and here if I said 161 to 320, meaning I'm extracting what is the LLTF received at the receiver. Okay, so this is a time domain received samples of, obviously it is faded from the channel. I have not considered AWGN in this case for simplicity. So this is has a fading effect on it. So now in the previous experiment we have seen in 1:16, that is in 160 samples of LLTF. First 32, 1 to 32 you have, that is a prefixed data. 33 to 96th sample, that is 64 samples we have. I think I have a figure for that. Yes. So this is experiment 3. Again, if you want in detail, you can revisit this. What I'm trying to tell here is this is the LLTF plotted, power of LLTF symbol plotted versus sample number. Here, if you see, the pink thing is from 33, sample number 33 to sample number 96. The green is from sample 97 to sample 160. So, but the last 32 samples, so we have seen in OFDM what is cyclic prefix. So if you want to know more on cyclic prefix, what is OFDM, please go to the video which I have attached. It's a discussion for OFDM and the importance of cyclic prefix to overcome ISI, etc. So here 32 is the cyclic prefix length. So 32 samples, last 32 samples corresponds to 129th sample to 160th sample. So this 32 samples are taken and it is prefixed, meaning the same thing is placed here. So the sample number 1 to 32 is same as sample number 129 to 160. Okay, and these two are repetitive. Okay, the 33 to 96, the pink thing and the green thing from here to till end, these are same, it is repetitive. But last 32 samples is taken and prefixed. So this is given by standard, it is standard specified. With now 2.11 standard specifies the LLTF training sequence, what it should be, and this is specified by the standard. So now that is what I have mentioned here, indices, and I have written this has to be same because the transmitted are same. The received thing also should be same. And discard CP, meaning what I'm doing, first 32 samples I'm discarding. So if you can see, if you can remember in OFDM what was done, yeah, here with CP you do data serial to parallel conversion, you do IFFT at the transmitter. So in our case WLAN waveform generator is already doing this, right? And you have a CP. So the LLTF inbuilt, the transmit LLTF add CP in it, right? So now at the receiver, I'm going to receive CP, then do FFT, right? And then detect. So IFFT is done at the transmitter, FFT is done at the receiver. So before IFFT, I have the complex modulation symbols. It can be from MQAM or MPSK. This is X of K. Here this is loaded onto the K subcarrier. So here you need to do a frequency domain view for this. When you do IFFT, you get the complex samples. It's a time domain signal transmitted over channel. You have a corrupted time domain signal coming in. Again, you do endpoint FFT, you get the recovered constellation symbols. So before doing this, you need to remove CP. So for LLTF, the CP was 32 length. So first 32 thing I'm discarding. So this is after discarding. So now LLTF demodulate. WLAN HE demodulate, there is a function. So you pass LLTF RX to it and then you get LLTF demod. Okay. So This I showed just to explicitly without CP, but WLAN HE demodulate, you can send the complete LLTF RX, that is the 160 samples. It internally does the discarding thing, and at LLTF demod is 52 cross 2. Okay, this is LLTF RX, what it is the received time domain signal. WLAN HE demodulate does FFT on it at the receiver end. Then you get demodulated frequency domain signal. So LLTF demod is a demodulated frequency domain signal. It is 52 cross 2. So 52 is the number of occupied subcarriers and 2 is the number of OFDM symbols. So in order to know more on that, let's try to get the OFDM information of LLTF. So yes, when you evaluate this, there should not be semicolon. Yeah. So the FFT length for LLTF is 64 because this forms the legacy part of the packet preamble. The FFT length is 64. But when you go to HE data field or HE part of the packet, for example, HE LTF and all, there the FFT length is 256. But because LLTF comes in the packet legacy part of the packet preamble, it helps in packet detection and other stuff so that the other devices, 802.11 devices, get to know whether it is 11AX or 11N. The first legacy portion has to be decoded. Hence, FFT length for the backward compatibility, the LLTF portion FFT length is 64. The CP length is 32. We saw this, right? 32, the last 32 complex samples was repeated in the first 32 samples. The number of tones, the occupied tones is 52. In addition to this, we have 12 subcarriers or tones which is not used. That is first 1 to 6, right? First subcarrier to 6th subcarrier, 33rd subcarrier, and 60th to 64 subcarrier are null subcarriers, which is used for synchronization and other purposes. Data is not being transmitted. So data transmission happens only on 52 tones and they are called as active frequency indices. Okay. Then in that, data tones are 48, pilot tones are 4. So 64 subcarriers, 64 FFT is used, CP length is 32 for LLTF field. So coming back, you remember, please remember those things. It is 64 point FFT and it is 52 occupied subcarriers, which includes pilot as well as data subcarriers. So coming back to this, yeah. So when you send LLTF RX, WLAN HE demodulator does FFT, and LLTF demodulate, we have 52 cross 2. As I told, 52 is the number of occupied subcarriers. So now for the estimation of channel, okay, I use LLTF field. So now LLTF demodulate, I use a WLAN LLTF HE channel estimate, which is already available in the toolbox. So to that, I'm going to send LLTF demodulate. So LLTF demodulate we obtained just now by making use of LLTF receiver waveform, and this is 52 cross 2, and send the channel bandwidth. You have the channel estimates. So I have the channel estimates. This because LLTF demod was 52 cross 2, EST will be of length 52. So now what I'm doing, I'm inserting a 0 in between. And then 1 to 26, I keep as it is, inserting 0. 27 to 52, I'm taking the remaining samples. So I'm plotting now. So I'm setting KK as minus 26 to 26 and do the stem plot and see how it looks. So yeah, so I've inserted 0 here in between center. So I'm not considered other. Actually, the center thing will be 0. Then the first to 6 and the 60 to 64 I have not considered. I just wanted to, they actually can set it to 0 and visualize, but I wanted to see how well the channel estimation is being done. So I have ignored the null subcarriers and considered only the occupied subcarriers. So the first plot is the estimated CFR using WLAN HE demodulate, that is for doing FFT of the received LLTF waveform, and then WLAN LTF channel estimate function does the channel estimation on these occupied subcarriers. The next what I'm going to do, I'm going to write or use own code for channel estimation and see how it works. So YK is LLTF demod. So I have the demodulated data, which is 52 cross 2. LLTF demodulate data, what was it? LLTF demod took the LLTF RX and it did the demodulation. That is, it did the FFT operation. So this is 52 cross 2 complex time domain samples. So that is, from that I am taking first column and storing it in YK. Then this is standard defined. Okay, this LLTF field is BPSK modulated. So LLTF lower, that's 26 points, are either plus or minus 1. Again, LLTF upper is again 26 points, either plus or minus 1. So this is BPSK modulated constellation symbols. Remember, this is before performing IFFT at the transmitter. So whatever we represent capital XK, that is the constellation symbols, right? Constellation symbols obtained from some constellation. So LLTF standard defined, it is BPSK modulated signal. So it is takes either value plus or minus 1. So this is performed before performing IFFT. Okay, this is standard defined LK. So now what I do, I define LKK, okay, which is LLTF lower, LLTF upper, and obtain, estimate channel impulse response from this. Why do I do this? Because this YK is after the signal has at the receiver, you have the received waveform and you have done FFT at the receiver and then obtained this LKK, sorry, YK. So YK, if you remember, YK is after performing FFT, after performing FFT of the received waveform, you have this YK. But LK is, which I know standard defines this. So I'm making use of that thing and I'm simply taking the ratio. This is something like, to explain in a simple terms, we know signal XK, and because for OFDM, just now we have seen that OFDM converts the narrow wideband signal into parallel narrowband signals, and y of n is simply at the output. Y of n in time domain is x of n convolved with h of n. In frequency domain, y of k is simply x of k into h of k. So my objective is to obtain this h of k. So what do I do? H of k is simply y of k by x of k, right? So I'm using simple least square estimation, wherein this is yk, that is a received thing, and this is xk. Xk is something like pilot symbols, which is already know. So this is estimated hk. So yk is a receiver thing, which is received at the receiver. Lk is the pilot symbols which is being transmitted. So I'll take the ratio of it in order to get the estimated hk, and I'm going to plot this. That is the second plot, which is obtained by using the simple fact that y of k is equal to h of k into x of k, and h of k is equal to y of k by x of k. So if you can see, they are matching. And now lastly, what I do, I know the impulse response which I have stored in IMPR. So I'm going to plot that. So IMPR is the time domain impulse response. I take FFT on that and do FFT shift. So why I do FFT shift? FFT I have done because FFT of h of n gives h of k. But when I do FFT shift, it shifts the zero frequency component of DFT to the center of the spectrum. Or in other words, it arranges the Fourier transform outputs into a zero frequency centered spectrum, so that it makes analysis insightful. For example, sometimes you may have to check whether the spectrum has even symmetry or odd symmetry, something like that. In that case, rearranging the outputs is more useful and insightful. So hence FFT shift is done. Then I'm plotting HK from IMPR. So here if you see, I've taken 64 point FFT. So again, I'm neglecting first to sixth component, that is the index points. Then 59, beyond 59, that is 60 to 64, again I'm neglecting, and I'm inserting a 0 in between, because for otherwise it is not a fair comparison, because here also I have plotted only unoccupied 52 subcarriers by neglecting the first 6 tones and last 5 tones, and I have inserted 0. Same thing I need to do here. I need to insert 0 in between, neglect the last 5 tones, and neglect the first 6 tones. So that is being done here. Otherwise, if you don't do this, there is a mismatch, and it is, you have to take 64 point F50. So therefore, I'm neglecting first 6, last 5, and I'm setting a 0 in between, and I'm just comparing this. So this is a DFT of the actual channel impulse response. That is a third plot. So I have used make use of subplots so that it is easy for comparison. If you see, this is the estimated CFR using HED modulate, which basically does the F50 operation at the receiver, and WLAN LLTF channel estimate. This is the code, own code written. So both the matching. So basically, WLAN LLTF channel estimate is also doing the least square estimation. We have some papers or references which tell the least square estimation channel estimation scheme performs better in IEEE 802.11 devices, even in medium and high SNR regime. So the simple least square estimation is used, computationally simple, but it is more accurate. So even WLAN LLTF channel estimate and this, they are matching. And lastly, the DFT of the action channel impulse response is plotted. So all three are matching. And I think here, yeah, I would have got this, I have already told. And here it is, what are the data points, what is the value, and what are the values at the pilot subcarriers. So finally, I'm saving the code so that I can use anytime. I'm saving it as a datemat file so that I can use it later. So this is the code. So here, before coming to this experiment, it is better you listen to the OFDM discussion, which is being done in order to get a better idea. So the basic aim of the objective of this experiment was to know what is OFDM, how it is being realized, and also to get the channel estimation of channel estimation, or to obtain the channel frequency response on occupied subcarriers using the LLTF field of the packet preamble. In practice also, this is being done. Initially, the LLTF field is used for the channel estimation in order to decode the pre-HELTF field of the packet. Then HELTF field is used. They are also called as mid-umbels in a high velocity scenario, or in when the receiver is, or when there is a receiver is moving. Then the HELTF field, that is the mid-umbel, they're also called as mid-umbel, that is used for channel estimation. This is because LLTF field estimation happens only once at the beginning of the preamble. But when there is a velocity, because of the Doppler, the channel may vary fast, right? In that case, the channel estimate, whatever you have done using the LLTF field at the beginning of the packet, may get outdated. In that case, you may have to do the channel estimation again, because when there is Doppler, the coherence time of the channel decreases and the channel varies fast. So you have to use the channel again, do the channel estimation when the PPDU transmission happens. So that is why during the PPDU transmission, you can again do channel estimation using HELTF field. They're also called as mid-umbel. HELTF field occupies 256 subcarriers, and you can do channel estimation. There, the F50 is 256. But in LLTF, the F50 was 64.F50. Thank you.